Okay, so this is a set of notes on volumes of revolutions and volumes of known cross sections. Okay, so the basic idea here is that if I'm in the graph and I have some function f of x, and I'm going to take a chunk of that function between a and b, that gives me an area here. And then what we're going to do is we're going to rotate that or revolve that chunk, right? So basically down here, I have another piece, right? This is here. And I'm going to rotate or possibly envision this as revolving that chunk kind of around something, usually the x-axis, right? So I've now done that, and I end up with a solid. So I end up with something that's kind of like a cylinder that's a little wavy here. It's a little wavy, little wavy, little wavy, little wavy. Got a circle on the end here, right? Got a circle back here. Oh, that's an ugly drawing. Let's see if we can't make this a little prettier. Um, hmm. Let's try maybe some tools here. Let's see, maybe we can make an oval there. No. Make like an oval here. There we go. Another oval here. And then we're crossing in front. Right? And it's got a little wave here at the bottom. And it's kind of crossing in the back there. So you get the idea, I think. There's actually a pretty good drawing of it in the notes. Maybe I'll present that drawing here. There we go. There's the drawing from the notes. You can see the curve there. The curve gets reflected down here. And I did a pretty good job with a pencil. I'm basically trying to find the volume of this. Okay? So the idea of how this works is we're going to take slices of this. And each of these slices is going to be a circle. And we're going to accumulate the area of those circles from A to B. So this is basically an accumulation problem. Okay, so let's get back to the chalkboard here and kind of see if we can make sense of this. All right, so what we're doing here is an accumulation from A to B. So this is going to be the integral from A to B. And what am I accumulating? I'm accumulating circles. So that's pi r squared with respect to x. But remember that r here, the distance from here to here at each x, is actually f of x. So this is the integral from a to b of pi times f of x squared dx. So this is how this kind of plays out. And this is going to give me a volume. All right. So let's look at a specific example. Okay, so really simple example. I'm going to let y equal x, and I'm going to take this, I'm going to revolve that around the x-axis from x equals 0 to x equals 1. Okay, so let's see if we can do this. Basic idea, here's y equals x, right? So this is 0, here's 1. I'm basically going to take that, and I'm going to revolve that around the x-axis, which is essentially going to make that cone. Okay, so according to this, this would be the integral, pi times the integral from 0 to 1 of f of x, which is x, dx, but it has to be x squared, right? Because it's pi r squared. Okay, so that's, let's get some space up here to work. That's pi times 1/3 x cubed from 0 to 1, which should be, let's see, pi over 3 times 1 minus 0, which just makes this pi over 3. And if you think about that, that actually makes sense because the volume of a cone is 1/3 pi r squared h. This cone has a radius of 1 and a height of 1, which makes the volume of the cone pi over 3. So the geometry and the calculus line up. Woohoo. Okay, so that actually gives some credence to what we're doing here, given that we can back this with geometry. All right, so let's look at another example. Okay, so let's say I take the curve x squared, right? So that's a parabola, x squared. And then I take the curve x cubed. X cubed goes up faster, right? And I'm going to take this between 2 and 4. So I've got like this chunk here, all right? Got this chunk. And I'm going to revolve that chunk around so it's like a chunk going this way. I'm going to revolve that around the x-axis, and that's going to make like this hollow trumpet kind of thing, right? So it's going to have like sides here, right, that go along and go in a circle, and kind of makes like the bell of a trumpet. Okay, so let me back up a lot of that unnecessary art there and just look at the chunk itself, right? So my game here is I want to take the volume of just that. So if I didn't have like that inner x squared, that would be like pi times 2 to 4 of x cubed squared. But then I'm going to take away this inside part. So that's going to be minus x squared squared dx, right? So this is pi times the integral from 2 to 4 of x to the 6th minus x to the 4th dx. And in the notes I did a whole bunch of work with this. Got a little really crazy number there because this gives me like pi times 1/7 x to the 7th minus 1/5 x to the 5th, right, from 2 to 4, which is like pi times, wow, these numbers are awful, 81,920 over 35 minus 77,168 over 35 minus, so this is all one quantity, 640 over 35 minus 224 over 35. Oh, this is awful. If that breaks down, it breaks down to 336 over 35 pi. You could check my work here, which ultimately is approximately 6,672.383 cubic units. Okay, so we really don't have to have the three-dimensional drawing to work this out. We just have to say that like the big radius is going to hit x cubed, the little radius hits x squared. We subtract them to get what this is when I revolve it around the center, and I get my rotation. Okay, so let's work one more where they don't give me the lower and upper bounds. Okay, so what we're going to do is we're going to say, well, what if I have the line y equals x and the parabola y equals, that's not a parabola, I'm getting sloppy here. The parabola, there we go, y equals x squared. And if I take that segment and rotate it around the x-axis, what is the volume of the rotation? Okay, so it doesn't give me the bounds, but where do these things bind? So if I take x and set that equal to x squared, that gets me x squared minus x is 0, which is x times x minus 1 is 0, which means that x is either 0 or x is 1, which means that this point of intersection happens when x is 0, and this intersection happens when x is 1. So if I'm going to rotate this around the x-axis, I'm going to take pi from 0 to 1 of, let's see, the outer radius is going to be x, so it's just the x, but I got to square that, minus the inner radius, which is like x squared squared dx, right? So this is pi from 0 to 1 of x squared minus x to the 4th dx, right? So Let's clear some of this clutter out. Okay, we'll delete that and turn that off, and let's keep mathing a bit here. So this is pi, the integral, oh, we're going to get rid of the integral here, right? So this is pi times 1/3 x cubed minus 1/5 x to the 5th from 0 to 1, right? So that's going to give me, whoops, let's see, if I put the 1's in there, I'm going to get 1/3 minus 1/5. If I put the 0's in there, I get the 0's. So this is pi times 5 minus 3 over 15, which should be 2 pi over 15 cubic units. All right, so there you go. The last type of problem here we get are what are called known cross sections, and these can trip people up a little bit. So let's spend a little bit of time on one of those problems. Okay, so in a known cross section problem, you usually know the shape of the base. So we're going to say that the base here is x squared plus y squared is equal to 4. Okay, so if you remember a little bit of geometry here, that's a circle with a radius of 2. Right? So the top part of this circle, let's solve this in terms of y. Right? So this gives me y squared is equal to 4 minus x squared. So y is plus or minus the square root of 4 minus x squared, which means like the top part of the circle here is the square root of 4 minus x squared. The bottom part of the circle here is negative square root of 4 minus x squared. Okay, so we're going to take cross sections that are perpendicular to the x-axis. And we happen to know the shape of these cross sections, and in this example, these cross sections are squares. Okay, so they have 4 congruent sides and 4 congruent angles. So what we're going to do is each of these cross-sectional squares is a different size, you see, depending on where the x value is. Okay, so what we got to do is we got to kind of figure out what the area of that square is in terms of x. So the area of that square, well, if I look at this, going from here to the end is 4 minus x squared, and going from here to the end is 4 minus x squared, which means the length of the side of this square is 2 times the square root of 4 minus x squared. And since it's a square, this is 2 times the square root of 4 minus x squared, right? So the area of the square should be 2 times the square root of 4 minus x squared squared, which means that, what do I get? 4 times 4 minus x squared, which is 16 minus 4x squared. So the area of the square is 16 minus 4x squared, depending on which x value I'm at. Okay, so that gives me the square. Now what I'm going to do is I'm going to add up all these squares. And I'm going to add up all these squares from where to where? Well, I have to start at like -2 here, and I've got to go to 2. Okay, so just like in the volumes of revolution, I was adding up circles, I'm now adding up squares. All right, so let's get us a little bit of room to work here. All right, so let's trash, oops, that's an oval. I don't want an oval. I want a rectangle. All right, so let's turn that off and then there we go. Turn that off, turn that back on, and trash this. Okay, so boom, gone, space. All right, so let's see. I am now going to find the volume, right? Get rid of that. Okay, a volume by taking the integral from -2 to 2 of 16 minus 4x squared dx. Okay, so let's see. This is 16x minus 4/3 x cubed from -2 to 2. Right, so this is going to give me, let's see, that's 32 minus, right? So that's 8 times 4 is 32 over 3. minus negative 32, right? And then this one becomes plus 32 over 3. So a little bit of work here. That's going to give me 64 plus 64 over 3, which works out to be 128 over 3. So that's a minus there. That one's minus, right? It's minus and then minus. So 64 minus 60, yeah, there we go, is 128 over 3. And yeah, that's it. That's the whole shebang. So this would be the area of adding up all of these little squares from -2 to 2 that are sitting on top of that circle. So I ask you to spend a little bit of time with that, see if you can make some sense of all this. Try a couple of problems. We'll work on some of this in class. But there you go. Volumes of revolution and known cross sections.